The scenes which follow are taken from a communist propaganda film, now being shown in America for the first time.
CBS Television presents a special report on Sputnik 1, the Soviet space satellite. Douglas Edwards reporting.
Until 2 days ago, that sound had never been heard on this earth. Suddenly, it has become as much a part of 20th century life as the whir of your vacuum cleaner. It's a report from man's farthest frontier, the radio signal transmitted by the Soviet Sputnik, the first man-made satellite as it passed over New York earlier today. Whir of your vacuum cleaner. Whir of your vacuum cleaner. Whir of your vacuum cleaner. Whir of your vacuum cleaner.
I want to put some closure on this vacuum question. This is the my third book I ever published.
Oh, okay.
It's called Just Visiting This Planet.
All right.
And it's a collection of Q&A. I had a column with a pen named Merlin. People ask fun, really playful questions.
That's cool.
And I collected, this is like decades old, but there's some timeless content in here. Somebody asked about the vacuum.
Mm-hmm.
Can I read?
Yeah, go ahead, please.
Am I loud?
Well, you can't read otherwise.
Okay. Here we go. The best vacuum you will find anywhere. I wrote this 30 years ago.
That's cool.
The best vacuum you will find anywhere, according to 4 out of 5 vacuum retailers and 5 out of 5 astronomers, is the void of intergalactic space. But we can then ask, is intergalactic space nothing? No, it still contains space. If you feel obliged to call intergalactic space nothing, then you must invent a word to refer to the region outside of the universe. In this location, where we presume there to be no space, there can be no nothing.
Wow.
Let's call it, we're left with no choice, nothing.
Nothing.
A place where there's not even nothing.
It's the nothing. Wow.
Hey, curious kids. Kevin here. Today on A Place Called Space, we are talking about the vacuum of space. What is a vacuum, and is space really a vacuum? The real definition of a vacuum, like what we're talking about, is a void of matter. It comes from a Latin word that means vacant. So there you go. A vacuum is nothingness. And this almost emptiness creates extremely low pressure. Fluids, like gases and liquids, like to flow from high to low pressure. In low pressure, the fluids can disperse or spread out more, like this balloon. There is higher pressure on the inside, and if I let it go, the air wants to go to the low pressure outside. That's like space too. If there is a hole, hopefully not in a spaceship or in a spacesuit, the air wants to rush out into the extremely low pressure of space. It's not a good thing. So what causes this low pressure space vacuum thing?
Are you sure there isn't a toilet? What's through this door?
No! Go through that door!
Oh dear, that was a bit silly.
Entropy of an isolated system not in equilibrium will tend to increase over time until it reaches a maximum equilibrium level.
If you keep the door open between 2 adjoining rooms of different temperatures, the cooler room will become warmer, and the warmer room will cool down until they both reach the same final temperature.
So the second law states that a spontaneous process generates entropy and involves heat moving from a hotter body to a colder body. Now, a refrigerator doesn't violate the second law of thermodynamics because it's not a closed, isolated system. We're continually inputting energy in the form of electricity to try and keep the inside of the refrigerator cold, but at the expense of the surrounding environment. So if we turned off the electricity, then eventually the air inside the refrigerator would come into thermal equilibrium with the surrounding environment. So the concept...
Take a gas, vacuum of equal volume, and we're going to remove the barrier. You know what's going to happen spontaneously, right? The gas is going to fill the available volume.
Is the expansion of a gas into a vacuum. I have in one of these bulbs some bromine, and in the other I have a vacuum. And if I open the tap between these two, you will see spontaneously the bromine rush from one to the other. Now that is the simplest change we can have, perhaps, because all that happens is a change in entropy. In this case, the expansion into a vacuum, nothing else is involved. There's no energy change, there's no temperature change, there's no change except entropy.
Can't have gas pressure without a container. If the sky was a vacuum, where the space agencies claim to be in space, then the gas we breathe would fill that space. Fill that space.
And if I open the tap between these two, you will see spontaneously the bromine rush from one to the other. Now that is the simplest change we can have, perhaps, because all that happens is a change in entropy.
The ultimate and most dangerous test was a huge, specially constructed vacuum chamber.
They were able to pull all the air out to create a big vacuum, just like it would be on the moon. That way we could test our suits to make sure there was no leakage.
One such test narrowly avoided disaster. Jim LeBlanc was the test subject in the vacuum chamber. Cliff Hess, the supervising engineer outside.
Jim, while you're exercising, I'd like you to stay intermediate all the time, okay? I'm pretty cool right now. Okay, well, you'll warm up here in a minute, so let's stay right here if you can stand it.
The testing started just normally, like they all do. And Jim was at a vacuum in the spacesuit.
I feel pretty good here.
With all the air sucked out, all that protected him was his pressurized suit. Then something happened.
I heard over the headset that he was losing suit pressure.
The tube pressurizing his suit had become disconnected. He was in serious danger.
There really wasn't any feeling. It was just happening so fast, trying to get the chamber back to a safe pressure and Jim to a safe pressure. He was inside the suit.
As I stumbled backwards, I could feel the saliva on my tongue starting to bubble just before I went unconscious. And that's kind of the last thing I remember.
Essentially, he had no pressure on the outside of his body, and that's a very unusual case to get, and there's very little in the medical literature as to what happens when you have that. There's a lot of conjecture, that your fluids will boil.
Within 25 seconds, a co-worker, sitting in a partially pressurized antechamber and wearing an oxygen mask, was able to dash in. At the normal rate of repressurization, it would have taken 30 minutes to make the chamber safe. Hess repressurized it in just over a minute.
That's much, much faster than you would ever come down in an airplane. It would really hurt your ears if you did that.
Finally, it was safe to let a doctor in. Miraculously, LeBlanc had already regained consciousness.
When I stood up in the chamber, I felt fine. My ears ached a little bit from the course of rapid repressurization, and that's basically the only effect I had.
You know, this was one of the few instances where anybody was ever exposed to that low of a pressure and lived to tell about it with no obvious damage.
Such an accident in space would have been fatal. But thanks to testing like this, no astronaut has ever had to face a similar situation.
So space is not a perfect vacuum. It's close, but it is better than any vacuum we can create here on Earth. We can try our hardest, but we aren't able to create a space vacuum. We can suck as much air as possible out of the chambers, yet a space vacuum is definitely going to be better.
We live within a pressurized system.
Scientist Evangelista Torricelli is well known for his discoveries related to pressure, among others. He is in fact the inventor of the barometer.
The pressure of a gas is the force that the gas exerts on the walls of its container.
Well, it's gravity. Matter attracts matter, the things that everything is made up of. So the majority of these particles, the matter, group together to form our stars, our planets, and our space rocks. Now this grouping of matter created higher gravity, and all of the space left in between the big pieces of matter, the space in between the stars and planets and space rocks, is basically empty, giving us the vacuum of space.
We look out in the universe and 85% of all the gravity that's out there has some mysterious unknown source. We add up all the stars, the galaxies, the planets, the comets, the black holes, the dark clouds, everything out there that we can see, touch, smell, or taste. And it doesn't add up to give us the gravity that we see operating in this universe. So really we should be calling it the dark force, because we don't know if it's made of matter. It could be a profound misnomer, sending people off in thought directions that might not really be the right path. So dark matter is just simply what we call this thing about which we know nothing, responsible for 85% of the gravity of the cosmos. We've known about dark matter since the 1930s. Back then it was called missing mass. That's what it was called, because there's got to be some mass. Where is it? We can't find it. It's got to be here somewhere, because we got the gravity. If you have the gravity, you got to have the mass. Mass and gravity go together. It's really dark gravity. Actually, we shouldn't call it anything. We should call it Fred. Something that has no meaning, because we don't know what it is to call it. But it is the longest standing unsolved problem in modern astrophysics. Dark matter, dark energy. Everything we know about the universe, what we're made of, galaxies, stars, planets, that's all right here. So, according to this chart, we are 96% stupid. We are 96% stupid.
Reification, fallacy, is a fallacy of ambiguity when an abstraction, abstract belief or hypothetical construct is treated as if it were a concrete real event or physical entity. Can you determine gas pressure without containment? Yes, inside a gravity field. The air pressure at sea level on Earth is about 1,000 millibars.
We are 96% stupid.
And space pretty much seems like nothingness, right? I mean, besides the stars and planets and space rocks, it's basically empty. But that's the thing. It's basically empty. Not completely empty. There are particles in space. NASA says there's about 1 to 10 particles per cubic meter. So that's a really big area and not many particles. There are also protons and electrons in space. That's the radiation, the things that humans and electronics don't like. But it's very low density. Some places it's a lot higher, so we have to be careful. The space in space is actually called the interstellar medium, and it's a plasma of hydrogen and helium.
You may have learned about the 3 states of matter, solid, liquid, and a gas in a previous lesson. Did you know that there is a 4th state of matter, plasma? In this lesson, we will learn about plasma. Recall that in a solid, all of the particles are closely packed in a fixed position, and therefore has a fixed shape and volume. The particles in a liquid are still touching one another and are able to move around each other. Therefore, a liquid still has a fixed volume, but it takes the shape of their container. What is the change of state that occurs when water is heated to 100 degrees Celsius? Pause, think, and continue when ready. The answer is water evaporates from a liquid to a gas, in our case, water vapor. The particles in a gas are further away from one another and take the shape and volume of their container. For certain substances, if we continue to apply heat to their gaseous form, another change of state could occur. These substances can go from a gas to a state of matter called plasma. For this change of state to occur, very strong heat must be applied. When heat is sufficiently strong, the electrons are stripped from their respective atoms, creating free electrons and positive ions. Although there are both negative and positive particles, plasma is neutral overall, as there are equal amounts of oppositely charged particles. Since free electrons are present, substances in plasma form can conduct electricity. This is what separates a gas from plasma. All gases cannot conduct electricity, but plasma can. Naturally occurring plasma include lightning and the northern lights.
One thing, you have a theory about the moon, and we expect to be able to get observable facts about the moon fairly soon. What is your theory?
Well, it is by now rather more than a theory. 10 or 11 years ago, I stated to various scientists that the moon is not a piece of rock, but it is a plasma phenomenon, cosmic plasma, and that this fact will eventually be confirmed. I made certain predictions which were already confirmed in 1958, and the situation now is coming close to a complete confirmation.
What will be the result if you're proved to be correct in your theories?
The result will be profound and decisive, because it will give proof that a complete re-investigation of the laws of nature is necessary. Because if the moon is a plasma, no man will ever land on it. Soft landing attempts will all fail. That means that the mass of the moon is far less than is currently assumed. It's in a different state of energy, and it has far less mass. That means there is no more explanation for the tides. If the moon, for example, had only 1,000th part of its current mass, then the tides would only be 2 inches high under conventional theories instead of sometimes 14 feet. And that means that if it is proved that the moon is a plasma, then all gravitational theories are out, and the new concept of the cosmos and of its laws has to be.
Dark matter is a mathematical placeholder. Astronomers estimate that roughly 85% of all the matter in the universe is dark matter, meaning only 15% of all matter is normal matter.
One of the greatest challenges that astral scientists and researchers face before they can fully understand the universe is so-called dark matter. Originally called the missing matter, dark matter is the name given to particles that don't absorb or emit light, making them impossible to detect through observing electromagnetic radiation.
We are 96% stupid.
But what if the object in question did not absorb, refract, or reflect electromagnetic radiation at all? How would you determine if an object was really there? This essentially describes the biggest challenge in finding dark matter. Since it does not emit or absorb electromagnetic radiation, it cannot be detected or observed directly. Further clues to the existence of dark matter came later, when scientists examined the glowing disks and halos that are present around galaxies. Astronomers also made estimates about the distribution of dark matter by studying the inexplicable movement of certain stars. This is how scientists explain the existence of dark matter. According to Newton's law of gravity, stars orbiting the center of a galaxy should slow down the farther they are from the center. However, look at the actual data of how stars spin in a galaxy. You will find that there is no significant difference between the velocities of stars near the galaxy center compared to those much further away. The most commonly accepted explanation for this phenomenon is that huge spherical halos of dark matter surround the visible matter in galaxies. It is this dark matter that keeps galaxies gravitationally intact. Here's an amazing fact. The matter that makes up all the known galaxies and stars only accounts for 5% of the universe's content. The vast majority of matter in the universe is actually dark matter.
Why has nobody been to the moon in such a long time?
Because we didn't go there, and that's the way it happened.
I'd go to the moon in a nanosecond. The problem is we don't have the technology to do that anymore. We used to, but we destroyed that technology, and it's a painful process to build it back again.
Apollo computer had 32K of fixed memory and 2K of erasable. That was it. No screen, no sound, no icons, no nothing. Just, and the keyboard just had, it had 0 through 10, read, clear, and enter. No graphics, no screen, no. On its best days, it couldn't get to 1 megahertz. So it was slow and weak, but it got its there.
I haven't seen anything that indicates the telemetry data is even in existence, and as I said, even if we had it, we don't have the machines to play it back.
Right, we've been unable to track it down. I mean, we don't know
where this telemetry data ended up, and we don't know what path it may have taken. So unfortunately, I'm afraid I can't really give you much of a clue as to where this data ended up and whether it still exists or not.
NASA admitted that it had lost the original footage of man's first steps on the moon.
The most heralded, most famous accomplishment of mankind, of humans, the landing on the moon. NASA lost everything. They're claiming there's nothing in their archives, nothing in storage, nothing in a cardboard box someplace that has anything to do with the Apollo missions. It's all gone.
Could the gloves the astronauts wore on their pressurized spacesuits have actually worked on the moon?
What I do is I pull a vacuum in this chamber I created, and I have a glove inserted inside of it. And it was to prove that the flexibility they shown in their suits and gloves are impossible. Right now, I can put my hand in there and I can move it every which way. I can grasp, I make a fist, I can lift up, down. But as soon as I throw this switch here, I evacuate the chamber.
As air is sucked out of the machine, the vacuum makes it more and more difficult to move the glove.
And this glove doesn't want to move. I can't bend it backwards. I can hardly force it down. I mean, how could you pick up small screws and bolts like they've shown them to do, or trigger a little tiny trigger on a camera with the glove doing this?
If it seems impossible to operate a camera properly in pressurized gloves, how could these perfect pictures have been taken?
This is Douglas Edwards. Good evening.
But we can then ask, is intergalactic space nothing? No, it still contains space.